Good afternoon. Thank you for the opportunity for presenting our work on linking carbon and water cycle. I'm sorry that I could not come in person because of some unavoidable reasons. Hence, I am recording my talk and it will be shared with you. So my talk is on linking carbon and water cycle. As a civil engineer, we are mostly concerned with water cycle and we understand many component of water cycle, or rather we try to understand many component of water cycle. But the problem is water cycle is highly connected to carbon cycle and we cannot really separate out. And this is of course an emerging area in civil engineering as well as climate science or in hydrology. And there are quite a number of students from my research group who are working in this area. They are Nivedita, Akash, Dipan, Sachin, so and many other students who are working in this area. So when I start introduction, I'll start with one of the very famous statement made by Aristotle, the great Greek philosopher, who said that the whole is greater than the sum of its parts. And this is very important when you're talking about climate or hydrology or any kind of science that is associated with natural science or earth system processes. For example, let's say if you're talking about hydrology and if you don't understand precipitation, it does not make much of sense because you'll not be able to simulate what exactly is happening. And same thing is with water cycle. So we are very well aware of this figure of water cycle, which has multiple components like precipitation, evaporation, evapotranspiration, condensation, transpiration, and etc. etc. And many of us are trying to understand these processes. Now, at the same time, if you go to carbon cycle, of course, geologists and different scientists who are working mostly on the biogeochemistry, they try to understand the carbon cycle in terms of photosynthesis, in terms of respiration, in terms of ocean carbon uptake, in terms of soil carbon, and so on and so forth. But what has happened till 2000 or 2010, the research were kind of disjoint. The people who are working on water cycle, they are more focused on water, ignoring the carbon. And those who are working in the carbon cycle, they just considered water cycle in a very simplistic way. So the coupling of water and carbon cycle has not really taken place in climate science or in civil engineering. And that was one of the major research gaps. So considering that, let us try to understand in what way carbon and water cycle interact with each other. So let's say, and we have to understand this in terms of in terms of changing climate. So let us try to understand how this carbon climate feedback really works here. So let's say if there is an increase in atmospheric CO2, which is actually happening and because of which we are seeing global warming. So when there is a warming that is taking place, you can see here, we are trying to, uh, let me open my pointer here. So if there is an increase in atmospheric CO2, then what will happen? It will impact the climate, and this is which we are saying in terms of increase in extremes, in terms of warming, and so on and so forth. Now let us try to understand if there is a warming that is taking place. If there is a warming that is taking place, the vegetation react to it, and often at a very high temperature, vegetation reduces its photosynthesis capability, and because of which the carbon uptake from the atmosphere becomes lower, or the it affects the land carbon sink potential of the vegetation, and that results into again increase in the carbon dioxide. So it's a very kind of a positive feedback. It keeps on taking places here in carbon climate feedback. You can see here there is a positive sign, and this is something which has been very nicely conceptualized by one of the very famous scientists, Bonan, in his very famous book Ecological Climatology. Now there is another thing which is also kind of a bit neglected, but it's very important. This is the carbon. This is known as carbon fertilization. What does it? Let us try to understand what does it mean by carbon fertilization. So carbon fertilization means when the atmospheric CO2 increases, plants photosynthetic potential increases. That means plants can do much more photosynthesis with less use of water. So what happens? There is a stomatal conductance of water reduces, and because of which, with a small amount of water, they can actually produce the food or they can do the photosynthesis. So the water use efficiency increases when there is an increase in carbon dioxide concentration, and that results into increase in the gross primary production. So gross primary production of a plant means it sits photosynthetic capability or photosynthesis amount of photosynthesis. So this gross primary production increases. So that results into a greater uptake. So let us say trying to understand one side CO2 is increasing, that results into warming, that reduces the gross primary production or primary production of the plant. On the other hand, when there is an increase in carbon dioxide concentration, the primary production is increasing. One side decreasing, the other side is increasing. And what is the resultant? And here comes another things, because precipitation or water availability is one of the most complicated variable to simulate under climate scenario. So models are not very good in terms of water, in terms of simulating precipitation and simulating water. So the broad projections are not very clear what exactly is happening. And it is even more uncertain for the Indian scenarios. So it's not very clear what exactly is happening to the plant photosynthetic capability, because it depends on water. And there are quite a number of nature papers which has come very recently. So these are the two nature papers which talks about how carbon dioxide concentration or land carbon dioxide sink is associated with temperature, and the second one associated with terrestrial water storage. So one said that it's more associated with temperature, resulting and warming has significant impact on it. The other one said yes, it is associated with temperature, but it is more associated with terrestrial water storage. And an extension of the work again done by in another nature paper. So there is a series of nature paper which came on this specific area, trying to understand how carbon cycle is associated with water cycle, and that shows how emerging is this area. And there it shows that, well, yes, soil moisture is important, VPD is important, but they are related to each other. And if you consider that direct soil moisture impact, then it is quite significant for land carbon dioxide uptake potential. So that shows that the water cycle through soil moisture is significantly impacting the global carbon uptake potential. And even if temperature and VPD is actually affecting the carbon uptake potential, soil moisture is again playing a role there. So that really shows that the role of soil moisture is very important, and that also shows the importance of water cycle in terms of understanding the carbon cycle or the photosynthetic capability of the vegetation. Now, now let us try to understand what are the key science questions which we are trying to address, and probably I'll try to address some of them in this talk. And my research group has been trying to address some of these science questions. The first thing is very straightforward, very simple question: what are the key hydrometeorological variables that affects carbon dioxide uptake by plants from the atmosphere? That's a very important question. The second question is that what are the likely impacts of warming on vegetation carbon dioxide uptake? That means if there is a warming, how does it affect the photosynthetic capability? The third one is, yes, what is the role of carbon dioxide fertilization? That means increased carbon dioxide results into increased photosynthesis, how much it is. Then fourth one is, if in one case if it is decreasing, the other case it is increasing, then what is the resultant? And the fifth and the one of the very important questions specifically for India is that what is the potential of vegetation and forest in India in terms of carbon dioxide capture or carbon dioxide uptake? Because India is the second highest contributor to global greening after China, and India is hosting two of world's 8 hottest biodiversity hotspots. Among these world's 8 hottest biodiversity hotspots, like Amazon is one of them, India is hosting two. One is the Western Ghat biodiversity hotspot, and the second one is in the northeast. So, what are the implications of climate change on the carbon dioxide uptake of this major forest? So, let us try to understand each of these questions. So first we are trying to understand, let's say if you consider a short-term variability, let's say monthly to interannual variations, let us try to understand what are the role of different climate variables on the vegetation productivity. At this moment, I'd like to mention that I showed some of the nature paper, and one of the nature paper was in 2017, where it was shown that the total water storage has significant impact. Total water storage means mostly the groundwater storage they wanted to mean. This groundwater storage has significant impact on the carbon dioxide uptake by the vegetation, because we are essentially talking about deep rooted forests in the tropical region, and that was one of the major conclusion of that Nature paper. But the kind of analysis that was being performed, that does not really lead to any kind of causal inference, and that was one of our major doubt. So I doubt may not be the correct word, maybe we are not very confident in accepting that total water storage is directly impacting the net photosynthesis. So what we tried to do is that we focused on India, and we tried to get the meteorological variables, the total water storage from satellite, and the vegetation related information from the Moody's satellite data sets and Moody's derived data sets. So if you look at it, this is the gross primary production. So gross primary production means the photosynthesis, and you can see there is a periodicity, which is because of the seasonality, and this is 2001 to 2019 data set. This is the um, this is the respiration, maintenance respiration by the plants, and if you are considering the photosynthesis minus respiration, that is net photosynthesis, and these are essentially the climatology. So this is some sort of data, and if you take out the anomalies, then this is some sort of an anomaly. We first tried to get the anomaly, and we can see there is a significant variation. So you can see, even if you take out the anomaly, if you take out the seasonality, there is a significant variability in net photosynthesis, and we are trying to understand what are the climate variables that affects this variability of net photosynthesis. And um, and essentially, where we have used the causal method, which is known as PCMCI, Peter Clark MCI method, which is a very solid and robust statistical method that can find out how one variable is affecting another. So let's say there are five or six, five time series A, B, C, D, E, and if I'm trying to understand that if the variability of A is causing the variability in C, then we have to use PCMCI to try to understand. Or if variability of B is causing the variability in D, then we need to use this kind of methods. Even it also tells us, let's say if the variability of A is affecting both B and C, then the other statistical method will show B is causing C or C is causing B. But PCMCI can really find out this co-founder, and then sort of taking out the confounding effect of A. So this is one of the advantage of using PCMCI. I'm not going into the details of the mathematics, but that's the way we normally do. Now, coming directly to the results. So what we have found, we tried to apply PCMCI, and this is to the photosynthesis. And this kind of arrows are showing the causal arrows. And this kind of arrows are showing the real-time connection or covariability. So if you look at it, you'll find that precipitation is affecting GPP. That means water cycle and carbon cycle are related. But we are unable to get total water storage directly affecting GPP. And why is it happening? So if you consider the Indian vegetation, it's mostly the cropland. If you're considering the Indian greening, that has happened because of the cropland, because of the agricultural intensification, which is mostly shallow rooted. When there is shallow rooted, that and if it is in the Kharif season, direct impacts of precipitation are immediately visible through photosynthesis, and because of which you are getting precipitation to GPP. Of course, there are irrigation that is taking place, but precipitation increases TWS, that increases photosynthesis. At the same time, decrease in TWS means more groundwater irrigation that results into photosynthesis. So this positive and negative kind of sort of neutralize each other, and so you may not get a TWS directly impacting GPP, but precipitation directly GPP you are getting, and precipitation is of course affecting the total water storage. Now, if you are considering the respiration, of course, temperature and respiration, they are highly related. LAI and respiration, they are highly related. And hence, the resultant, you can see that precipitation is directly controlling the net photosynthesis. And temperature and net photosynthesis relation it does not have a direction. So they are co-varying. So that clearly shows that if you are considering the Indian vegetation, the monsoon rainfall is one of the major significant thing that is affecting the gross primary productivity and net photosynthesis. But we do not have a very strong connection with the total water storage, which has been found in the Nature paper. For Indian condition, it's slightly different because of the India's land use land cover pattern. Now the second question will come, when you're talking about the vegetation productivity, it goes through stress period. And majority of the stress comes because of the different climatic condition. And there are two such stressors. One is, of course, deficit soil moisture. When soil becomes very dry, vegetation cannot really continue the photosynthesis. And the second one is because of the increased vapor pressure deficit. Vapor pressure deficit means atmospheric aridity. When the atmospheric humidity reduces, then the evapotranspiration increases quite significantly. And when evapotranspiration increases quite significantly, you need huge amount of water to really continue the photosynthesis, and because of which the photosynthetic capability reduces. So we are trying to understand which one is the most major governing factor. Is it soil moisture or is it atmospheric aridity that affects the primary productivity of the vegetation in India? When we performed a very simple correlation, we have used the satellite data of SIF, which is known as solar induced chlorophyll fluorescence, which is some sort of a measure of the photosynthesis. And when we compared with SIF versus soil moisture, when soil moisture increases, SIF increases. And when VPD increases, that means vapor pressure deficit increases, soil photosynthesis decreases. But these two correlation cannot really tell you that which one is affecting what or in what way. Because soil moisture and vapor pressure deficit, these are the two variables which are strongly connected with each other. How? Because when there is an increase in soil moisture, evapotranspiration increases, vapor pressure deficit reduces. And when vapor pressure deficit increases, that results into increase in evapotranspiration and soil moisture decreases. So there is a very strong coupling between soil moisture and vapor pressure deficit. And hence, if soil moisture is affecting SIF, if not VPD, but you will still get a correlation between SIF and VPD. So simple correlation does not really tell you what exactly is happening. So we have to work in a different way. And this is what we are trying to find out. First, we did a conditional test. So we are trying to understand, given conditional on VPT, how SIF is dependent on soil moisture. And you can see that very strong partial correlation between soil moisture and SIF. And that clearly shows that when there is an increase in soil moisture, SIF reduces, given a constant VPD. But given a constant soil moisture, SIF versus VPD association is not very strong over India. And there is a reason behind it. Because in Indian region, the time when the vegetation productivity is highest, that is during the monsoon time or post monsoon, when the VPD is not that high. And probably because of that, it's mostly driven by soil moisture. And if you take the difference of both, you can see that mostly green means it's mostly driven by the soil moisture. The second thing also what we did, we first regress SIF with VPD. So we take out the VPD component from SIF and then try to find out its correlation with soil moisture. You can see there is a very strong correlation with soil moisture. But when we are doing the opposite thing, the correlation is not that high. That clearly again shows that soil moisture is a dominating factor in controlling the vegetation photosynthesis in India compared to vapor pressure deficit or temperature kind of things. This is again for the interannual or monthly variation. This is not about long term. We have to understand that because we are taking out the trend and performing this kind of analysis. And their differences shows that it is driven by soil moisture. Now, this is about the interannual variations, but let us try to understand what exactly happened over the longer term. And so for that, again, we have considered MODIS. Over the last 20 years, we are trying to understand what is the trend of primary productivity. Here, I'd like to mention that there was an HR sustainability paper in 2019 where it was very clearly mentioned that India is the second highest contributor to global greening. And if you look at um, the trend of leaf area index, you will find that everywhere there is a very strong positive trend that shows that there is a greening that is taking place over India. But let's say if you are looking at gross primary productivity, which is a measure of photosynthesis, or net primary productivity, which is photosynthesis minus the total respiration, then you will find that there is a decreasing trend over certain regions in India. And if you look at it very carefully, the decreasing trends from MODIS data are observed over the Northeast India, the Western Ghats, the two among the 8 global biodiversity hotspots. and also over the peninsular India. So these are the regions where you can clearly see that there is a decreasing trend, and of course there are certain regions which are increasing trend. But the major forest over India showing a decreasing trend of NPP, which is not a very good thing. So let us try to understand what exactly is happening. So what we try to do here is, so we try to check what are the trend of other meteorological variables. When you looked at it, what we have found is that the regions, you can see Western Ghats, Northeast, and the Peninsular India, these are the regions where warming trend is quite significant in India. This is the air temperature trend. So the regions where we are getting a decrease in the vegetation productivity, those are the regions where there has been a significant warming. So let us try to understand that why warming results into this kind of decrease in the net primary production. So I'll just show you what exactly is happening. Let us try to look at region 1, what is happening. So when your warming keeps on increasing, your photosynthesis keeps on increasing, but after certain temperature it starts dropping. So there is a threshold temperature above which the photosynthetic capability of the vegetation drops, but your respiration keeps on increasing. So what is happening? Your carbon dioxide uptake is reducing, but carbon dioxide release is increasing, and that results into decrease in the primary productivity. And it's everywhere. So if you look at it, you can see that for each and every, let's say if you're considering 4 and 5, you can see that respiration keeps on increasing beyond 25 or 26 degrees centigrade, but your photosynthesis drops quite significantly. And these are the regions where you can see a very significant decrease in the net primary productivity. So it again clearly shows that if there is a warming, that warming has significant impact on the productivity. And this is the work which has been done by one of my student, Ripan. But there is certain thing also we'd like to mention here is that the kind of data which you have considered here, this data does not consider carbon fertilization. So Moody's products does not consider carbon fertilization. It just considers the impacts of meteorology. So, and carbon fertilization may have significant impact, as I was telling. So the next question is that what will be the likely impacts of carbon fertilization in India in terms of vegetation? And because no observed data is available, so what we have to do is that we have to check it with the model simulations which are available from CIMIP6. And this is what is being done by one of my other student, Nivedita. So what she tried to do is that she was analyzing different model output, and she was trying to understand that if we increase your carbon dioxide concentration by 1% every year, at the end of the day, what is happening? Is your GPP is increasing or GPP is decreasing, or what exactly is happening? So when you looked at it, of course, you can see that with the increase in carbon dioxide concentration from different model, so you can see the carbon dioxide concentration is increasing from 300 to 1200, and when it is ppm, and when it is increasing that, you can see that there is an increase in temperature. Vapor pressure deficit is slightly increasing. Precipitation. One of the good thing is that the model started saying that if there is a warming, the monsoon rainfall will increase. So this is consistent across models, but models have serious limitation in terms of simulating Indian summer monsoon rainfall. So you have to be a little bit careful. And with the increase in carbon dioxide concentration, temperature increases, so evapotranspiration is increasing. Soil moisture is slightly increasing because of precipitation. These are important things. But what is happening is that you can see the GPP is increasing. And water use efficiency. As I said that because of carbon fertilization, water use efficiency is increasing. So good thing is that your you're not getting water stress from the, at least from the model simulations, because it shows that with warming the monsoon rainfall will increase and your carbon fertilization is increasing. So because of which your models started showing that in the future the vegetation productivity will increase in India. And the other very interesting thing what has come out is that, you know, for the same, so these are essentially the GPP for drought condition, and you can see at a higher carbon fertilization for the same drought scenario, your GPP is increasing. So earlier when the GPP anomaly value was negative, that is becoming as high as 20 for different model simulation, and that clearly shows that GPP will remain will be unaffected if there is a huge carbon fertilization that will take place in India, which is a very good news for India if the model simulations comes true. This is really good because the impacts of drought and vegetation will be much reduced because of carbon fertilization in India. But of course, we have to believe the models, or I hope that the models are really doing well, and models need a lot of improvements as well. Now, but what exactly happened is the observed condition, and that is something which we are not very sure. So we thought of, okay, let's do one thing for the observations of our the observed data set. Let us perform our regional simulations and trying to find out what exactly is happening. So we have taken a NOAA LSM model, which is a land surface model, which is coupled with weather research and forecasting model, and we have considered three cases. One is the standard one, CO2 is increasing from 2004 to 2018. For the second one, we kept the carbon dioxide concentration at 2004 level, but allowed the climate variables to change in their own way, the way they change in the observations. And the second one, we are making it to 2022 level. Now, when we looked at it, uh, the just the impacts of carbon dioxide concentration, we can see of course temperature we are seeing majority it is increasing, but the important part is that if you look at it, we are finding that GPP and NPP in the observed condition has not really increased. This is what is very important. That shows that over the last 20 years period or last 18 years period, carbon fertilization probably took place, but carbon fertilization could not really result into increased GPP or NPP because warming has its own impact that reduces the GPP and NPP. But water use efficiency, of course, has increased. Now, the second interesting part also we wanted to find out whether the soil moisture dominance will increase or decrease, because we know that for Indian vegetation, the soil moisture is actually dominating over the other stressors, which is vapor pressure deficit. So we are trying to understand if the soil moisture dominance will increase or decrease in a carbon fertilization condition or increase carbon dioxide concentration. And what we are finding is that soil moisture dominance will further increase if you increase the carbon dioxide concentration from 0.4 level to 22 level, and you can see that it is increasing. That means in a increased carbon dioxide concentration, water and carbon cycle are becoming more and more connected to each other. They are getting more and more coupled, and that clearly shows that if you really need considering water cycle or carbon cycle, now there is no point of considering them separately. You need to consider in a coupled way, and that's the future of water cycle or hydrological modeling. So the future directions, I would say that I'll not really list down the conclusions which I have derived till now, but what I'd like to say is that there is a huge problem in the data. We mostly rely on the observed data from satellites, and there are very few ground truth verification, and most of the cases data is not available. So what is needed is that India needs significant number of in situ flux observations with the data available to the scientists. Otherwise, there is a huge scope of research that is possible, but the researchers in India were unable to perform research or unable to publish in very good journals simply because we do not have very good in situ flux observations, widespread in situ flux observation we do not have, and even if we are having, their data is not available. That is one of the major problem, and that needs a revolution in this country. Secondly, of course India has developed the art system model, IITM art system model, but it should have a very strong component of even terrestrial biogeochemistry. It has a very good oceanic biogeochemistry model, but terrestrial biogeochemistry is important. And finally, we need to understand and simulate water and carbon cycle together. Considering them separately may not really add value at this moment. So thank you for your attention. Thanks. And thanks for the opportunity.